pattern change assessment. So this will include the truck trips. And it will be displayed in a GIS in terms of the color and the thickness of the line. So originally we have the choke point right here. So you can see the after, you cannot use that link. So the pattern is changed a little bit, okay? Because this is only for one origin destination pair. But you can actually look at for the whole. Okay, so now I'll talk about the case study that we did. This is for the Utah Highway Network. And as I mentioned in the beginning, the scenario that we're going to be doing is based on an earthquake scenario. So what we need to do is get all the bridges because we want to focus on the bridges. So the database that we are using is called the National Bridge Inventory Database, short NBI. And in this database, there are many things, but the things that are of interest to us are there are four components of the bridge, which is the superstructure, the deck, the culvert, and the substructure. And this is how, in the U.S., how they define whether the bridge is safe or not, based on these four structures, okay? And there is a condition rating, and it goes from 0 to 9. And if it's less than 4, it means that the bridge is structurally deficient. So meaning that the bridge may not be safe for at least one of these four components. So what we did is that we go to this database for the state of Utah, and then we sort, to find out how many structural deficient bridges are in the state of Utah. And this is what we got. So there are about 221 bridges that are considered as structurally deficient. I don't recall how many bridges in total, but it's probably in the order of thousands. So there are 221 as of 2004, and these are the location that has a rating at least in one of the four components with a rating of less than 4, okay? And we just classify these bridges according to the conditions. So you can see majority has a rating of 4. There are some that is 0, which means that is completely failed, okay? And most of this are in the deck structure. So this is the deck, and this is a superstructure, and this is the substructure and the culvert. So majority has to do with the deck. So recall what's the deck? The deck is basically this part, okay? And also the superstructure and the substructure. And then we also classify according to functional class, and there are 16% that are in the interstate freeway. And there are many that are actually in local street, okay? And this is for the rural area, and in the urban area, that percentage increased to 48%. And what we did is that to define the scenario, we have to overlay this to the seismic hazard map, because we are doing this for the earthquake scenarios. So we obtained the seismic hazard map from our colleague in the structure group at Utah State. And basically, this is based on this what they call peak bedrock acceleration map, and is measured in peak ground acceleration, PGA. And basically what we did is out of those 221 deficient bridges, we selected the location that are on the location that are with a high PGA to define as a scenarios. Okay, and then basically what we did is we run a bunch of scenario, and we divide it into 3 rural interstate bridges, urban interstate bridges. These are single bridge scenario. So what happened if one bridge fail? okay, either in the rural area or in the urban area, how does it affect the whole state? Okay, and then we also run a case with multiple bridges failure simultaneously, because when there's an earthquake, there may be more than one bridge fail at one time, and you can see the impact of multiple bridges failure. So this is the scenario A and C. This is for the rural area, okay? A is right here, so you can see the Google map right here. And this one is on I-70, Interstate 70, and this is really in the rural area, in the middle of nowhere. So if this bridge collapses, there's really no close alternative, okay? And then this one is in here, same, is in the Beaver County. So we run the scenario A, and this basically we remove that bridge from the database, and then we run it. This shows you the OD connectivity, and recall for the whole state there are I think 48 zones, 29 within, and then also there are 19 external stations. So this is a 48 by 48 matrix, and you probably cannot see the numbers because we're trying to show the whole matrix in one slide. And what we did is we color-coded. So basically, this will show you the detour length, So red means that the detour is higher, and yellow is probably medium, and if you don't see any colors, means that it's not being affected by that one bridge, okay? And so you can see with one bridge failure, you can see that it affects multiple places, okay? And here we just show you one of them in a GIS map. So this is for a particular OD pair that go from this county to the external station, okay? So the bridge is somewhere around here. So you can see that they have to take a detour, and the detour basically is 60-mile increase compared to the original one, okay? And this one from here to here, there's a 52-mile increase, so that you can actually visualize, due to one bridge failure, how does it affect many different OD pairs in the network. And this one shows you the freight flow pattern change. So here we show in terms of the thickness of the line and also in terms of colors. So you can see that this one is right here. So you can see that there's going to be a problem over here and over here. And this one is over here, and so on, okay? And the next scenario is for the urban bridges. In the urban area, there's a lot of alternative, so it may not be such a big problem. So basically, we selected some bridges on the interstate. So one is here, and the other one is near Salt Lake City. And we run the OD connectivity, and you can see that when we remove that particular bridge, basically the impact is very low because there's alternative in the urban area, as opposed to the rural area, there's not much alternative. And then this is the freight flow pattern change. So there's a minor impact on the flow pattern, but compared to the rural area, is not that significant. And this one, we run for the multiple rural interstate bridges. So multiple bridges fail at the same time. So in this case, you can see that there's a lot more red, So the impact is much higher when you have multiple bridges fail at the same time. And same for the freight flow pattern change. And so as a summary, So what I did is I presented a research framework for assessing transportation network vulnerability. We developed a decision support tool to facilitate the process of analyze vulnerability, and then demonstrated with you for a case study using the Utah Highway Network, particularly on how to make use of different databases that are available. So we did not spend any money like collecting data. We don't have the 10 million like in Korea to actually do survey. We just use whatever available provided by the government, different government agency from the national, from the state, or even from local jurisdictions. So what are some of the potential applications? When I present this to a DOT, I mentioned there are 3 potential applications. One is bridge management. So as from the case study, it's very clear. You can actually use the case study to prioritize for the repair. The other 2 are operational planning and also security planning. Security planning is like this because every few years the government, especially at the federal highway, require the planning to include additional things. And one of the issues is security. So for the new requirement that they're asking the planning agency or the DOT is that you must include a security planning for your travel forecasting process. And they don't really have a clue exactly what they're supposed to do. So this could be one of them, which is to look at in the case of if there is a disruption, whether that's man-made or natural disaster, do you have a backup plan? Okay, so this is for long term. And the other one is for operation planning. These are for the people who are managing the daily traffic conditions. And if there is a disruption, perhaps short term, what they have to do is show you what are the detour routes. So they would like to know, okay, if this bridge is not available or if this route is not available, what are the detour routes that they can use? So this is for the operation part. And this is the bridge management, and this is done by Taiwan, my master student. He just finished. So he actually used this software to add another module to do the bridge prioritization. And basically what we did is we used some economic cost and impact score. It's a very simple method. It's basically you have different criteria and then you define the weight, but making use of this software to give you some of those attributes, so that you can actually calculate the total score and prioritize. So you can see there's different ranking for the different bridges according to whatever the criteria that you define. And finally, this one, I thought that how do we actually adapt the software in the case of Thailand? Earthquake is not such a problem in Thailand, but flood is a problem. And here, you can see that I'm not exactly sure what is the location because one of my students did this for me. And I believe this is from maybe last year or the year before. And you can see flood situation, and then you have the truck that moving through. It's fairly dangerous to do that, And this is for the rail network. So you can see basically you cannot move because the water is already quite high already. And are these the potential bottlenecks here that kind of connect the north and the south? So anyway, you can run this decision support too for the case of floods, so that you can either come up with alternative plan if there's no alternative routes. Okay, with that, I conclude my presentation. Thank you.
Thank you very much. I did a similar sort of research, and I found that the one OD connectivity vulnerability or other measure is very sensitive to the network coding. So if for a certain link that we may not actually include in the analysis, or also the location that we define as the origin and destination, and I mean this kind of sensitivity issue, how can we address if we can apply this framework to say Thailand, and where the database of the network model is a bit limited.
Okay, thank you for the questions. With any analysis, the input data is very important. So this is the so-called garbage in, garbage out. So if you have garbage data, then obviously you're going to have garbage result. But the question that Akachai is asking is that, the coding issues, and it may be sensitive for network coding. But this particular question is actually dependent on the purpose of the analysis. So if you're trying to look at the whole Thailand, then probably you would only include most of the major routes rather than the minor arterial. So I think there's limited chance for you to make coding error from that respect. But in terms of the truck traffic data, I believe it's going to be a big problem because in Thailand, I'm not sure whether there is a freight analysis framework database or not. If there's no database, then you probably have to come up with some method of how to estimate the truck OD, and that I can tell you is very difficult and is also very costly. You heard from Dr. Park, it costs them $10 million per year to develop, to maintain. This is per year, and this doesn't include the labor costs and all the 25 PhD, salary. So I would say that, you have to make intelligent use of whatever that you have. And what this talk is trying to do is trying to make use of whatever the available database from the US, So for the case of Thailand, I'm pretty sure that you're going to have to do the same. And in some cases, you may need to do some survey to verify the accuracy, Otherwise, there's no way around it. Hopefully, I answer your questions.
So when you try to make use of the priority, like when to or what bridge to fix, as a user, have you thought about the fact that when you fix the bridge first, it's not going to be off use for a while? So you might not, you can think of the high order. Let's say you fix the bridge that is not off use first, so you can deviate the traffic that can somehow handle larger traffic first. So the overall disruption might be less than you were to think of it as just one, one order, if you will.
Right. In terms of the bridge management, there are many ways to do it. And what we chose to do is a very simple scheme based on different criteria. But I agree with you. A lot of time is that you may not want to just fix the primary or the most significant one. You want to fix the secondary one, and those may not be important when there's no problem, but it become important when there is a problem. So this has to do with how redundant is your network. So are there any redundancy in your network? So if you look at this particular one, you can see that this is the only route. You don't have a secondary. Okay, so you're going to have to focus on that one. But of course, if there is a secondary, you may be able to formulate, like say, for example, as a redundant optimizations, and look at secondary alternative when there is a disruption. So it's possible to do that.
Today in the afternoon, our first speaker, we are very honored to have him to speak with us today. He's Professor Dr. Art Shavalit Wong. Okay. He is right now a professor at Rutgers University, but earlier just this past semester he was a visiting professor at Princeton University, and he received his PhD degree from the University of Florida in the US. and he will be talking to us today about the topic of large-scale optimization of transportation networks, computational challenges, and recent advances. So please welcome